Oh my goodness, we are close to the end of this amazing topic of Calculus 1. This section, a bit more theoretical, a bit forward-looking, the mean value theorem. So this section is about a theorem. We are going to allow ourselves the opportunity to talk about things like proofs and analysis, and to look forward to how do we prove some of these big things in Calculus 2, or even that we've already learned so far. And in general, if a theorem has a name, it's probably important. It's probably a big... Suppose we've got some function. Let's break that down a little bit. I've got some starting point at a and some ending point when x is equal to b. And we learned at the very beginning of this course that we could think about the secant line in between those 2 points. And that secant line has a slope, and that slope is the average rate of change. Meanwhile, our function could be doing any number of wibbly wobbly things, while still, on average, having the same average rate of change as drawn here in this dashed line. What the mean value theorem guarantees us is that somewhere along this curve, the tangent line is parallel to the secant line. In other words, somewhere along this curve, your instantaneous rate of change is equal to the average. At some point, you were going the average. Now, with a couple of important rules, we need to know some things about our function before we can really say this, but this is all the mean value theorem says is, hey, in between a and b, there must be some point c such that the derivative is equal to the average rate of change, okay, or the slope of that secant line connecting them. A surprisingly important result in that it makes a lot of other things flow. It's kind of like the intermediate value theorem, which says that if you're continuous, you can't skip over any y values. Well, this is kind of the derivative version of that. It says, well, if you're continuous and differentiable, then you can't sort of skip over your average rate of change. That has to happen at some point. So we're going to build our way up to this. And what we're building up to really is a topic called analysis. When we start using calculus to tell us about the very nature of functions, like what is and is not possible, using proofs and derivatives and everything else we can think of. Usually this is called analysis, so there are classes like real analysis or complex analysis that deal with complex functions. Advanced math classes often focus on the proofs and the properties about why things are true, about functions, about numbers, about the world even. This is a nice little warm-up to a little bit of advanced mathematical thinking. I think it's appropriate towards the end of this first course in calculus to think about how a mathematician thinks about these things. Rather than getting right to the mean value theorem, we're going to have a lemma, something called Rolle's theorem, which is kind of like a baby version of the mean value theorem. It says, if you can guarantee the following three things: if f, my function, is continuous on a closed interval ab, if also f is differentiable, it has a derivative on the open interval ab, because functions don't have derivatives on their endpoints. The last condition just says that the endpoints agree. In other words, it's the same picture as above, where we're going at an angle, but instead of at an angle, if the endpoints agree, then the average rate of change is just 0. That secant line is horizontal. And so the result in this case is that there should exist some c on that open interval, some x value c, such that the derivative is 0. That's Rolle's theorem. And because we're being a little bit fancy today, I went ahead and I wrote it out in some fancier math terminology or math notation as well. It's good just to see it. This also says, then there exists c in AB such that f prime of c equals 0. In other words, this big backwards e is math symbol for there exists. This little other looking e thing is in, so it's for set notation. C is in this set from A to B. ST is an abbreviation for such that, and then f prime of c equals 0. That's not going to be on any test that I give, but it's nice to see these things before you actually need them. Okay, let's do an example of Rolle's theorem. If we take f of x equals x squared minus 3x plus 2 on the closed interval 1, 2. Let's check. Does that satisfy our three conditions? First, is f of x continuous? Well, it's a polynomial, so f is definitely continuous. Good. Is it differentiable? Yeah, it's a polynomial. Polynomials are differentiable everywhere. All right, and does it have the same value at a and b? Well, in this case, a is 1 and b is 2. So let's check. F of 1 is equal to 1 minus 3 plus 2 is equal to 0. And f of 2 is equal to 4 minus 6 plus 2 is also equal to 0. Didn't have to be 0, they just had to equal each other. And they do, so we are good to go. Rolle's theorem applies. And what this tells us is that there is some c where the derivative is 0. And just for this particular case right here, let's really work this out. What is f prime of x? That is equal to 2x minus 3. Is that ever 0? Well, yeah, sure it is. 0 is equal to 2x minus 3 implies that x is equal to 3 halves. And notice that 3 halves is in between 1 and 2. So Rolle's theorem just told us there'd be some point in between 1 and 2, and 3 halves is that value of c. Nice. It works. Or rather, in this case, it works. It didn't lie to us. Good job, Rolle's theorem. Let's look at an example or two that maybe don't work. So for instance, if I was going to look at absolute value of x, what does that look like? Let's draw this. Whoomp, whoomp. And here, I'll go ahead and add in something like that. It's a nice pointy looking thing. Notice that between 2 and 2, negative 2 and 2, yes, they agree. They're both 2. So Rolle's theorem would try to say that I should have a derivative of 0 somewhere, but in fact it's not. The derivative is negative 1 on the left, and it's positive 1 on the right. It's never 0, and the issue here is not that it's not continuous. It is definitely continuous. It's not that f of a doesn't equal f of b. It does. The issue is that it's not differentiable at 0. So if we don't have a derivative on the entire open domain, it doesn't work. Okay, let's just go ahead and write that out real quick. F prime of 0 does not exist. So no rolls. Okay, all three of those things have to be true at the same time. Tangent of theta in between 0 and pi. Well, if I draw a tangent of theta real quick, it looks a little bit like this. Okay, and in this case, just doing a quick sketch here. Because tangent has that vertical asymptote there, it's not continuous. So that discontinuity at pi over 2, notice that pi over 2 is in between 0 and pi, means we can't use Rolle's theorem. And you can check. Rolle's theorem is not satisfied, right? There is not a point where the derivative is 0 on the interior, so in between 0 and pi. It was actually positive the whole time. Okay, so there's 3 examples, one where it works, and we can actually find that c, and then 2 where it doesn't, one because it's not continuous, and one because it's not differentiable. But why does it work? Okay, I'm going to walk you through a proof because it's good for you, and because it's good to start seeing the actual arguments that lead to these theorems. And if you can remember the proof, then you'll remember that theorem forever. Okay, let's work through this proof. Get a taste of what a mathematical proof might look like. And the idea here is we want to show that there's a derivative of 0 somewhere. And I think to myself, where does that happen? Oh yeah, it happens at local maximums and minimums. So maybe I can show that one of those exists. And that's how this proof goes. We say, all right, we know that f is continuous on this closed interval. So we can apply the extreme value theorem. We build up theorems to prove other theorems. Because of the extreme value theorem, it has to have an absolute maximum and minimum on this closed interval. So now we're going to start just going through cases. How could this happen? So if the max or min is at some c in this open interval, then c is a critical number. That's what we call it when, well then, this is where the critical numbers have to happen. And if it's a critical number, then either the derivative is 0, which we want, or the derivative doesn't exist, which we don't want. And that's what Fermat's theorem tells us. Because it's differentiable, we know it has to exist. So the derivative is 0. Now, here's the part where a lot of people would stop because they're not as careful as mathematicians. We didn't actually take care of all of the cases. There's another possible case. So, if, on the other hand, the max and min are not on the open interval, they're not in AB, where else could they be? Oh, they could be at the endpoints. But if the maximum and minimum are at the endpoints, and A and B are the same, well, the only way that can happen is if my function is constant, right? And then there's a max and a min everywhere. And if it's constant, my derivative is 0. And that's everywhere, which would just count every single number in the interior, right? And that's the whole proof, right? We say, all right, this thing must have a maximum and a minimum on this closed interval. If it's in the interior, great, we're done. If it's on an endpoint, well, then the whole thing has to be constant. And so we really would have had one in the interior as well. And that's the proof of Rolle's theorem. One more quick example of what this means. Rolle's theorem tells us that a spring, think of something going up and down over and over again, it must be perfectly still at some moment. Why is this? Well, usually we'd say that the motion of our spring is some trig function, like cosine of t. But all those waves, those sines and cosines, those are all continuous and differentiable. And more than that, they're periodic. Right? So on some period, in this particular case, 2 pi, cosine of 0 equals cosine of 2 pi. That tells us that we can apply Rolle's theorem. Right? And in particular, you could actually solve for this, right? You know what the derivative of cosine is. It's negative sine, and you could solve for when is negative sine equal to 0. So even things that seem to be moving up and down unendingly, there's some moment in time where they're totally still. That's another way to think about what Rolle's theorem is telling us. Okay, next up in the next video, we'll move on to the more general case, the mean value theorem.